Hello, 8th grade. You're watching the video lecture for Lesson 1-4 from the Plate Tectonics unit. This is on seafloor spreading and subduction. So this first page here, guys, is our lesson objectives. And we have two big things we want to accomplish today. We want to be able to list evidence of seafloor spreading and be able to explain the process of subduction. Those are two things we want to get to today. And from before, we talked about the idea of continental drift in the previous section. And Alfred Wegener had all this evidence of how the continents did move. They looked like they had been in previous places before, but he couldn't say why. What was the force that was driving them? And so now what we have in this section is some of that evidence to support that, yes, the continents are in fact moving. So that evidence that the plates of the earth, that the continents are in fact moving. This section is going to focus on this evidence. Our first form of evidence is from what's called the sea floor spreading. And we get this idea from the Mid-Ocean Ridge. The Mid-Ocean Ridge is the longest chain of mountains in the world. The ridge curves like the seam of a baseball along the ocean floor. And we can see this right here. Here's a map of the earth. And we can see this Mid-Ocean Ridge. You can see it going right there through the Atlantic Ocean, Mid-Atlantic Ridge, through the Indian Ocean. Even goes through the part of the continent between Africa and Saudi Arabia there. Over here in the Pacific Ocean, here you see the Pacific up along to the coast of California. And so this Mid-Ocean Ridge is one of the big forms of evidence we have that in fact the surface of the earth is not stationary, that it's slowly moving, and in this case it's expanding. And so the Mid-Ocean Ridge is kind of the first big piece of evidence to suggest that this is where something's happening at this Mid-Ocean Ridge. And it wasn't until really World War II that we had sonar and had the ability to kind of map out the ocean floor. It was actually for military purposes first, to map out that ocean floor and find this Mid-Ocean Ridge. And so we didn't know it existed until the late 1940s into the 1950s. And so what happens here? What happens at this giant chain of mountains that goes around the earth? What happens here is volcanoes. It's volcanic activity. And molten material is rising from the mantle. And what's happening is, as it rises, it's actually pushing the older rock out of the way. So new rock is coming up from these volcanoes at the Mid-Ocean Ridge. And so seafloor spreading, just like it sounds, is this process where we are continually adding new material to either side of the ocean floor along that Mid-Ocean Ridge, that seam of the baseball you saw in the previous map. And the first time we actually went down there with cameras and saw this was until like the late 1970s and the 1980s. And what we found were whole ecosystems, these giant clams, these tube worms, were all around these hot sulfuric volcanic vents, places that would be toxic if we were anywhere near there, hundreds of degrees Fahrenheit or Celsius, and this toxic sulfur to us. But these ecosystems have developed there at this Mid-Ocean Ridge where these volcanoes are. So it's a process where we add new material through the volcanoes and pushes the older stuff out to either side. And how do we know? What are some of the forms of evidence we have that seafloor spreading is in fact taking place besides the volcanoes we can see erupting? What we have are these what are called pillows of rock on the ocean floor. So rock that cools really fast, like due to the ocean water, it forms what kind of looks like pillows of rock. One big form that we can map out away from the Mid-Ocean Ridge, are the idea of these magnetic poles have reversed. The North Pole wasn't always at the north. It's actually switched between the north and the south, have switched back and forth over the course of Earth's history. So, and there's a record of that on that ocean floor. So as new material is added and it cools, there's bits of iron in there, and that lines up in the Earth's magnetic field, and we can tell how old that rock is based on if the rock was facing toward the North Pole or the South Pole, that alignment as aligned toward the North or South Pole. We can kind of take those patterns out, starting at the Mid-Ocean Ridge, going farther and farther away, and dating the rock that way. So what we have here, whoop, I went too far. Here's a picture of the idea. Here's that Mid-Ocean Ridge, right here in red. That line right there. And what happens is, as the material moves away, down to the left or the right, when that polarity is switched, that record is trapped in the rock. And so as you go farther and farther away, these different stripes appear, telling if it was, how many, there's no real set pattern. There's a few 100,000 years, sometimes a million years between these flips. But that record is trapped equally on either side. So if we drill out equidistant to either side, that polarity is the same because it's pretty much adding the same amount to each direction. And so we can have that record of this sea floor spreading from the Mid-Ocean Ridge as it goes out each side. We can map out the polarity whether it be normal or reversed, on either side equally as it goes away. So it's really kind of a big piece of evidence we have that the sea floor is in fact spreading from that mid-ocean ridge. What we also have, you can see here's a map where we've dated that rock, the age. It's about the age of the rock. We have ways, the methods of dating rock. Carbon-14 dating is a big one. And you can see here the younger rock is in red, and all the red rock is near that mid-ocean ridge. Here it is in the Pacific Ocean. Here it is in the Atlantic Ocean. So all the newer rock is in red and oranges. And as it gets older, you can see here it's in green, it's older, down in your blues. So your oldest rock is farthest away from the mid-ocean ridge. Here it is in the Atlantic, and that older rock is farthest away from the mid-ocean ridge. Again, showing that the older rock is being pushed farther and farther away from the Earth, or from the mid-ocean ridge. Now, if this is true, if the sea floor is in fact expanding, wouldn't the Earth be getting bigger? So if we're adding rock somewhere, there's got to be somewhere else where it's kind of being taken away. And this happens at subduction zones. So subduction zones are where we have the feature on Earth would be a deep ocean trench, is where it happens. And this is where that denser ocean floor sinks into underwater canyons. So we get, just like it sounds, we get a canyon underwater. Some of the deepest parts of Earth are at these trenches. And so subduction is a process by which the ocean floor sinks back into the mantle. And at these deep ocean trenches, subduction allows parts of that ocean floor, as these two plates meet, they're kind of ramming into each other. The older one's going to sink down over millions of years into the ocean floor. And we can see that here. Here's a subducting plate. This is off the coast of North America, actually. So here's Portland up here. Here's Mount Hood. Here's Mount St. Helens. And the Juan de Fuca plate, it's a very small plate off the Pacific Northwest. And it's subducting. It's going back down. So here this plate's going down back into the mantle. And as it does so, some of the gases are trapped or released, and it melts, and a less dense material rises through, and it creates these volcanoes. So Mount St. Helens, a famous volcano here in the United States, had a major eruption in 1980. Mount Hood is another one that hasn't erupted recently, but these are both mountains. They're actually volcanoes that form after this plate subducts back down in there. Part of that plate will melt and come back to the surface. So these subduction zones are where the older plate is being pulled back down into the mantle. And again, with all these processes we've talked about, they happen very slowly. We're talking inches or centimeters a year, just a few. Think about how long your fingernails grow on average. That's about as fast as these plates move. So it's a very slow process in geological time. All right, 8th grade, I thank you for watching, and we'll see you guys along the way.